All right, so as I was saying in the previous video, again, heat transfer has three different ways in which it can happen. First one is going to be conduction, which is a heat flow through a substance from high temperature to low temperature. So in the picture, it's shown to you there by the transfer of heat from the main part of the pot throughout the handle of that pot. So conduction itself is not very relevant in the atmosphere, obviously, because things aren't necessarily touching each other in substances that are good conductors. So air itself is not a very good conductor. So although conduction does happen, it's not going to be very strongly so. So good conductors are things like metals, for example. So if you were to expose a metal to heat, it can very easily transfer that heat from one, say, edge where you're putting the heat next to the other edge of the metal, because that heat travels really fast through that metal material. Same with cold temperature. So if you expose the metal to the cold, it's going to get cold really, really fast. So I don't know if you have ever tried this, maybe you have. For example, if there's like a metal door or just a metal frame, and it is really cold in the morning, and then you sit on it or simply touch it, you feel that your heat, like your body heat, is instantly leaving you and just being transferred onto the metal frame or metal door. So that's kind of gives you a better idea of what conduction is. So as I was saying in my graduate research, I did a lot of work on conduction through soils. And one of my purposes was to see that like if different materials that contained the temperature measuring devices, so basically thermocouples or small sensors containing thermometers, if you would, how those thermocouples would react if they were encased in different materials. So if the thermocouples were encased in metal, then the soils would have been felt a lot hotter than they really were, because all of the heat from the surrounding soils would decide to basically go into that metal frame. However, when we tried the thermocouples to be immersed in materials such as plastic that is not very conductive, then the actual heat from the soils was accurate. It was what it actually was on the surrounding soils at the same depth at which the soils were at. So that is one of one of the purposes of the work that I did on my graduate research. And if you're curious about it, I'd be happy to talk to you more. So let me know. But anyways, second type of heat transfer is going to be convection. So convection is defined as the heat flow by the mass movement of a fluid, such as water or air. So just by that statement, you should be thinking that convection is a lot more important as a heat transfer mechanism in the atmosphere than conduction was. So you can think of these like mass movement of fluid. You can think of like smaller convection cells. So you can think of like volumes of space in the air that would constitute those like mass movement of that fluid. So if you think of all the air being split into these convection cells, some of the convection cells are gonna be warmer than others, and some of them are gonna be cooler. And so the movement of these specific convection cells relative to each other is going to constitute convection. So just like conduction, however, things move from high temperatures to low temperatures. Okay, so keep that in mind. So convection itself is going to be a very important process for the transfer of atmospheric heat in thunderstorms, and also in large-scale circulation of warm air away from the equator. Okay, so keep that in mind as we go on to the further slides. That will make it much easier to understand. Okay, and lastly, the third type of heat transfer that we experience is radiation. So radiation is going to happen as wave-like energy that is emitted by any substance that possesses heat. So as you're seeing, oh, I forgot to mention the image for convection. You're seeing here that like hotter temperature water cells, if you would, are moving upwards to the cooler place, and then the ones that are on the surface of the water are being displaced and moved downwards. And so the cycle continues and continues. So that happens both, well, in any fluid really, but it happens very apparently so to us in air and in water. Okay? All right, so again, for radiation, because it is the energy that is emitted by any substance that possesses the heat, you are seeing it in the image as the fire, which is the heating mechanism for this pot. So you're seeing that it happens in a wave-like way, so it produces these waves, and depending on the wavelength, you're going to get something that is hotter or something that is not as hot, or maybe something that travels faster, the heat is traveling faster than other things that are not. So the transfer of this energy by radiation occurs by oscillations in an electric field and a magnetic field. And so these waves are generally called electromagnetic waves. All right, so you might hear them be talked of in this way. All right, so for example, the type of heat that we receive from the sun is by radiation. Okay, so if you have questions about heat transfer and the 3 types of heat transfer, please clarify it in the book or online before we move forward, because that's going to be pretty key for the coming slides. So when we look at the Earth's energy balance, we can basically assume that 100% of the energy that is given to the Earth is going to be from the sun, okay? Although I told you earlier that there is part of the energy that is basically coming to the surface is coming from the core, the internal heat of the Earth, and again, that energy comes from radioactive decay of atoms. The greatest majority is coming from the sun. So if you go back a couple slides, you can see the numbers, and you'll see that yes, a very, very high percentage is from solar radiation. So having that in mind, and having in mind the first law of thermodynamics, which tells us that energy is neither created nor destroyed, it simply changes form, then we can split that incoming solar energy or solar radiation into different components that are either going to be absorbed by the Earth, reflected, or are going to stay within the Earth for a little bit and then later on leave. So as you're seeing in the graph, and I actually like the graph that you guys have in the book a little bit better, but the graph tells you that, again, all the energy is coming from the solar radiation. 25% of that energy is absorbed by the atmosphere. So that's these rays that you're seeing over here. 45% is absorbed by the surface. Oh, sorry. So that one just basically, where's my arrow? So that one basically stays, the first one, the 25% is going to be absorbed by the atmosphere and stay right here. 45% is actually going to be absorbed by the Earth's surface, may it be in the water or just like plants or urban or whatever it may be. And then 30% of that energy is going to be reflected back into space. From that amount that is reflected back into space, 25% is from the atmosphere directly, and then 5% is from the surface of the Earth. Okay? So basically, about 50% actually gets to the Earth's surface. From that 50%, 5 of it is being reflected. And then about 50% is actually staying within the atmosphere. 25 is being absorbed. And then the remaining 25 is being reflected back into the atmosphere. So that reflection in the atmosphere happens due to cloud cover, basically. And then the reflection at the Earth's surface happens depending on the different materials that the Earth has. And we went over this a little bit on chapter 12 on climate change. So if you need a refresher, go back to the slides from that chapter and maybe the narration of those slides so you guys get a refresher on it. So about 70% of the heat is being lost to space, as you're seeing on this part of the image right here. And then some of the heat is being reabsorbed by the Earth. So that is the greenhouse gas effect that we have seen again on chapter 12. So I'm not going to go in depth with it but again, if you need a refresher, check those slides out. Basically, some of the heat that is leaving the Earth is being reflected, is being re-refracted, and that heat is coming back onto the Earth due to that layer of pollutants of those greenhouse gases. Okay, so when we talk about energy that we're actually receiving from the sun, so again, that was what kind of energy? or what kind of heat transfer, I should say? Okay, radioactive, or radiation, sorry, not radioactive, should have been your answer. So I also said that radiation happens through electromagnetic energy, or that's another way in which people call it. So that is why this slide is named that way. But basically, this is going to be energy that is coming in from the sun. So as you might know, this is traveling at a speed of light, which is about 300,000 kilometers per second, so very fast. And then the wavelength, I should define this before we move forward, is going to be the distance between two waves. So if you are seeing, for example, this peak right here, this peak right here, or this ridge or valley, right here, the wavelength would be the distance between this valley over here and this other one over here. So you're seeing that the wavelength in this particular part of my graph is much larger than the wavelength in this particular part. Here is much smaller. Okay? All right. And so this image that you're seeing here is going to be the electromagnetic spectrum. And as you're seeing, it's very wide. It goes from wavelengths that have very low distances or very low wavelengths to some that have very large wavelengths. So as you're seeing also in this particular graph, the visible light spectrum is only one tiny fragment of that huge possibility of wavelength distances. So just to give you an idea, the overall incoming, or the overall energy that we receive from the sun is going to be from incoming shortwave radiation. So we are receiving energy from the sun in this kind of lower wavelengths. So that's why, for example, a lot of you have heard of ultraviolet light as being one of the things that the sun radiates our way, and we have to protect ourselves against it, because sometimes it can have some negative impacts on our skin, for example. And then the radiated energy back into space from Earth is going to be long-wave radiation. So long-wave radiation is anywhere in between infrared and radio waves. Okay, so that is what we, from the Earth, we radiate back into space. So we intake short-wave radiation, and then we output, if you would, long-wave radiation. So once this energy from the sun as short-wave radiation reaches the Earth, it can either be absorbed, as we saw in the previous image, or it can be redirected or transmitted, right? So many times the albedo effect takes place, and we have talked about the albedo effect before. So depending on what color, basically, things have, as they're receiving the energy, a certain amount of the energy will be reflected back into where it's coming from. So as an example, forests of pine only reflect 5 to 15% of the energy that they receive. Grasslands, on the other hand, because of their a little bit lighter color, reflect up to 25%. So also we've talked about this, but as you know, some of the gases will absorb certain wavelengths. So for example, CO2 and water vapor that are on the atmosphere will absorb the infrared energy that is transmitted from the Earth and then trap it. So again, because Earth outputs the long-wave radiation, part of it being that infrared energy, as it's redirected back into space, the CO2 and the water vapor will absorb that and basically re-radiate it back into Earth. So another thing to have in mind is that the hotter the object, the faster that it will radiate energy. Okay, the hotter the object, the faster it will radiate energy, which explains, for example, why the sun emits shortwave radiation, right? So because the sun itself is so hot, it emits this very fast energy, emits very short wave radiation. So the wavelength is very small because it's so hot. The Earth, because it's not so hot, emits long wave radiation. Okay? So again, the hotter the object, the faster it will it will radiate energy.